Hello, this is John Miares, and in this lesson, we are going to start exploring the inverses of trigonometric functions from the analytic, geometric, and algebraic perspectives. We've already done a little bit with inverse trig functions when we were working with solving triangles and doing problems involving the law of sines and law of cosines. Now we want to look at inverses as functions of real numbers and try to make connections with what we've been recently working with regarding the graphs, domains, ranges, and other properties of the six primary trigonometric functions. Now we're covering two sections here, but the material is pretty much the same between the two sections. This lecture, which unfortunately won't be a short one, would be just as long if I was covering just section 5.5 or just section 6.4, because there is that much overlap between the two sections in the text. The homework for these sections, I'm hoping, is actually going to be a lot shorter than what you've been dealing with so far. Before we begin discussing the inverses of trigonometric functions, it might be a good idea to do a quick refresher of what is an inverse function in general. Functions f and g are called inverse functions if f of g of x will simplify to just x for every value x in the domain of g, and g of f of x simplifies to just x for every number x in the domain of f. Essentially, whatever g will do to a function, f undoes it, and whatever f does to a function, g will undo it in order to get you back where you started if f and g are inverses of each other. Let's take this one for example. You have the function f of x equals 2x plus 1, and g of x equals the quantity x minus 1, all divided by 2. Let's think about what each of these functions does just verbally for a second. The function f takes a number, doubles it, and adds 1. The function g takes a number, subtracts 1 from it, then divides it by 2. If you were to take any number in the real number system and plug it into the function f, double it and add 1, then take the output of that function and plug it into the function g, you're subtracting 1, dividing by 2, you will get whatever number you started with because g does the inverse of what f does. Even the steps in the order of operations are done in the reverse number. You take a number, you double it, you add 1, then subtract 1, and divide it, you get right back where you started. If you wanted to see how this comes together algebraically, we can actually take f of g of x. To do that, we're going to take the entire formula for g and plug it into the function f like so. The function f says we want to take whatever's in the parentheses, double it, and add 1. So we're going to take the entire expression for g, double it, and add 1. Simplifying this expression, you should see that the 2's on the outside are going to cancel, leaving you with just x minus 1 plus 1, which after you cancel the 1's leaves you with plain old x, the number we started with. If we do this process in reverse, taking g of f of x, you're going to see a similar phenomenon happening. We'll take the formula for f, 2x plus 1, and substitute that into the function for g. The function g is going to take whatever answer is in parentheses, subtract 1 from it, and then divide the result by 2. Combining the 1's in the numerator leaves you with 2x over 2, which after we cancel the 2's leaves you with plain old x. Let's look at another example where we are verifying inverses, but this one maybe you can try on your own. Here, we want to show that the function f of x equals x cubed minus 1 and g of x equals the cube root of the quantity x plus 1 are inverses of each other. Go ahead and pause the video to try to work this one out. See if you can take f of g of x and g of f of x and get them to both come out to be plain old x. For f of g of x, we're taking the expression g, the cube root of x plus 1, and substituting it into the formula for f. The f rule says to take whatever's inside parentheses, cube it, and subtract 1. Cubing the cube root will eliminate the radical, giving you x plus 1 minus 1. Then canceling the 1's will reduce to just x. When we do it in the reverse order, the f formula is being plugged into the g rule. And the g rule says to take whatever's in parentheses, add 1, and then take the cube root of the result. When we do that here, the 1's are going to cancel first, leaving you with the cube root of x cubed, and those will undo each other, leaving you with just x. Let's think about how we might try to reason this out using logic and verbal descriptions. F of x takes a number, cubes it, and then subtracts 1 from the result. G of x takes a number, adds 1 to it, then cube roots the result. If you were to take any number, plug it into one of the functions, then take the result and plug that back into the other function, you would get whatever number we started with. So let's say we take the number 5 and we'll plug it into the function f here. So 5 cubed is 125 minus 1 is 124. Now if we take 124, I'll plug it into g here. So you have 124 plus 1 is 125. And then the cube root of 125 gets you back to 5. If these functions are truly inverses of each other, then this relationship of one function undoing the other will work no matter what number we plug into it and no matter which number we start with. Let's look at the graphical relationship between two functions that are inverses of each other. And hopefully, what we are covering is all review from Math 121 or from a previous course. Let's say we want to show that the two functions f of x equals x cubed minus 1 and g of x equals the cube root of the quantity x plus 1 are going to be inverses of each other graphically. Now notice I can also use this notation with the f to the minus 1 of x to describe that this function g is going to be the inverse of function f. Just a reminder, that notation, even though it looks like what I have as an exponent of minus 1, is meant to describe the inverse of a function, not the minus 1 power. We're not taking a reciprocal, we're taking the inverse of a function. There's a huge difference. Let's start by graphing f of x equals x cubed minus 1. This is the basic shape of the cubic graph that has been shifted down 1 from the origin. Notice that each square on this graph is actually half a unit, so don't get confused by it's going down 2 squares. Each square is half a unit. Some of the points on this graph are going to be 0, -1, 1, 0, -1, -2. Now these can be easily verified by plugging in these x values into the function and checking the outputs. Now let's look at the graph of g of x, the cube root of the quantity x plus 1. It has a very similar shape, but it's been flipped over sideways. If I look at it here, if I was to label some points on this blue graph, what you would find is we have the points 0, 1, negative 1, 0, and negative 2, negative 1. What I'm hoping you see is two things. First, that these two graphs are mirror images of each other over the line y equals x. Here, I've inserted the line y equals x as a dashed line so you can see how it acts as a line of symmetry between the two functions. What I'm also hoping you see is that if the function f contains the point xy, then the inverse function, f inverse of x, will contain the point yx. This ties things back to what we were discussing earlier, that if you were to take the output of one function, put it back into the inverse, you'd get right back where you started. So if I took f of 2, you would get 2 cubed minus 1, which comes out to be 7. And then if you took g of 7, that would turn into the cube root of 7 plus 1, or the cube root of 8, which equals 2. That tells me here that you're going to find the point 2, 7 on the graph of f, and its mirror image, the point 7, 2, will be on the graph of g. Now, when we're looking at two functions that are inverses of each other, there are some things we need to take into consideration to make sure that the inverse relation we have is going to satisfy the definition of a function. A function needs to be strictly increasing or strictly decreasing in order for its inverse to also technically be a function. Such functions are also referred to as one-to-one function. One-to-one functions have the property that not only is there one y value associated with each x, that's the definition of a function, but there's also only one x value associated with each y value. Graphically, such functions must pass both a horizontal line test and the vertical line test. So looking at these two graphs, both of these functions are considered one-to-one, or a fancy word, monotonic. X cubed is increasing on its entire domain. Cube root of x is increasing all the way throughout as well, although be it pretty slowly. Consequently, both of these functions will pass the vertical line test because they're both functions. Remember, the definition of a function requires for each x in the domain, there can only be one value y in the range. For a one-to-one function, for each y in the range, there can only be one x value in the domain, which can be verified by applying the horizontal line test. So this function is one-to-one because it will pass both the horizontal and vertical line tests. So we can say the function has an inverse or the function is invertible. So what happens when the function is not one-to-one? Let's say we wanted to find the inverse of the function f of x equals x squared plus 4. It seems that we should be able to come up with an inverse for this one. Just by reasoning it out, this function takes a number, squares it, and adds 4. If we look to apply the order of operations in the reverse order, in order to undo what f is doing, all we should have to do is take whatever number comes out, subtract 4, and take the square root of the result to get ourselves back where we started. However, this poses some unique issues. Let's recall how we can find the inverse of a function using algebra. We start with the given function in y equals form. So y equals x squared plus 4. To find the inverse, the first thing we would normally do is switch the variables x and y, then see if we can use the rules of algebra to turn this equation into y equals form. It should seem reasonable that all we should have to do is switch the order of the variables, because when we were graphing inverses, we saw that one graph had the point xy, the other graph had the point yx. If we can get the points on the graph by just switching the x and y coordinates, why not just switch the x and y variables in order to find the algebraic inverse of that function? To get the y by itself, we need to subtract 4 from both sides, and then we'll want to take the square root of both sides. However, if you recall from your earlier studies of algebra, taking the square root of both sides of this equation is going to introduce a plus or minus sign out in front of the radical. This wasn't an issue when we were looking at cubing or cube rooting in the previous example, because the cube root of a negative number is negative and the cube root of a positive number is positive. That isn't the case when you're square rooting, because when you square either a positive or negative number, you always get a positive result. Let's look at this one graphically then. Here's the graph of the parabola represented by the function f of x equals x squared plus 4. I know the inverse of this function is going to be symmetric to the original function over the line of symmetry y equals x. So I've inserted that here as a green dashed line. Now, if I reflect the entire parabola over the line y equals x, what I now get is this sideways parabola here. Now, we have worked with sideways parabolas. We did that back at the beginning of the course in chapter 11. But the problem is that this sideways parabola is not a function because it does not pass the vertical line test. We could have predicted this by looking at the original parabola and seeing that it was going to fail the horizontal line test. So those horizontal lines that cross the parabola more than once are going to turn into vertical lines that cross the parabola more than once we flip it over sideways. The challenge is this: it seems that this function should have an inverse to it, because verbally we can reason out what the inverse of this function is supposed to do, and algebraically we should be able to compute it. But analytically, graphically, we need to somehow fix it so that the inverse will be a function. That is, we need to restrict the domain of f so that it will be a one-to-one function, and we will still account for the entire range of f inverse. So there are multiple ways that we can do this, but the conventional approach when it comes to square roots is to assume that this root that I want will be the positive square root. So we'll remove the bottom half of our sideways parabola, and now the blue graph is going to pass the vertical line test. The corresponding change to the original function would be to remove the left half of the red parabola. So now we're only going to be considering positive x values. Now my red graph is going to pass both the horizontal and vertical line tests, making it a one-to-one function. When we look at some specific points on this graph, looking at the red parabola, we have 0, 4, 1, 5, and 2, 8. While on the blue graph, we have the points 4, 0, 5, 1, and 8, 2. Simplifying our result, what we say is that the inverse of our function f will be the square root of the quantity x minus 4 without the plus or minus in front, which will imply that I'm only interested in the positive square roots coming out of this function. So although the domain of the original function would normally run from negative infinity to positive infinity, and the range included all real numbers greater than or equal to 4, the inverse is going to have a domain that is x values all greater than or equal to 4, but the range is going to exclude those negative numbers. As a general rule, what you're going to see is as a result that when you're trying to find the domain of an inverse function, it will always be the same as the range of the original function when you reverse the x and the y's. However, when you want to find the range of the inverse, it always must be some subset of the domain of the original function f in order to guarantee that it won't fail the vertical line test. So let's see if we can now summarize what we should know about inverse relationships. As a general rule, for a function f whose inverse is denoted f to the minus 1, if f is not inherently a one-to-one function, its domain must be restricted so that it is not just a one-to-one function, but also so all possible values of the range of f are accounted for. This way, the domain of f inverse will be the entire range of f. This is important because I don't want to lose any parts of the red parabolas or the blue parabolas that would have had points potentially flipped over sideways. Also, the range of the inverse will be a subset of the entire domain of f. Now that we've looked at inverses of functions in general and gotten that refresher, let's talk about inverses of trigonometric functions specifically. After all, it does seem reasonable that trigonometric functions should have inverses. After all, there are buttons to generate these values on the calculator. And we've already discussed that intuitively, when taking the sine, cosine, and tangent of an angle, we get some number out that represents some ratio of sides in the triangle, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So when we take the inverse of that, we're plugging in that number or that ratio and working backwards to get the angle. So the sine of 30 degrees is 1/2. So the inverse sine of 1/2 would be 30 degrees. However, are any of the 6 trigonometric functions one-to-one? As I look at the graphs of y equals sine x, y equals cosine of x, or y equals tangent of x, it should be pretty obvious that these functions are going to fail the horizontal line test miserably because of the cyclic nature and repeating patterns inherent in their graph. Now the question becomes, what can we do about it? Well, maybe we don't need to worry about it too much. Let's grab our calculators and see what happens when we start evaluating some inverse trig functions here. Grab your calculator and see if you can give these a try. To help us maintain a good perspective, let's make sure our calculators are in degree mode before doing our calculations. So now I've got my TI-84 calculator emulator up here on the screen. So we're going to hit the mode button to make sure that we're working in degree mode so that when we do these computations, we're going to be getting the angles back in degrees. So I'm going to go down, radian, use the right arrow to go to degree, hit enter, and then second, quit. Now, as a reminder, the -1 in the notation is read and treated as an inverse and not as the reciprocal. So when we're looking at the first one, I'm not taking the cotangent of 1. We're looking at the inverse tangent of 1. Go ahead and pause the video for a minute and see if you can give these a try. So the first one, the inverse tangent of 1, should give you 45 degrees or pi over 4 radians. The inverse tangent of -1 will give -45 degrees or negative pi over 4 radians. The inverse sine of 1/2 is going to be 30 degrees or pi over 6 radians, while the inverse sine of -1/2 gives us -30 degrees or negative pi over 6. Now you might be sensing a bit of a pattern here, but with cosine, it's a little different. The inverse cosine of 1/2 is 60 degrees, and the inverse cosine of -1/2 isn't -60 degrees, but rather 120 degrees or 2 pi over 3 radians. Now let's think about that for a second. 120 degrees is in quadrant 2. It is a 60-degree reference angle, but in quadrant 2, cosine is negative. So the cosine of 120 degrees equals -1/2. If we look at -60 degrees, which is in quadrant 4, well, in quadrant 4, cosine is positive. So the cosine of -60 degrees is going to be +1/2, not -1/2, which is one of the big reasons why this angle can't be -60 degrees. Let's look at each of these from the functional perspective. If I was to graph the function y equals sine x, we get the sine wave that we're all familiar with. I've left the axes labeled with integers rather than with multiples of pi here because it will be easier to interpret things when we look at the inverse and flip things over sideways. But if you consider that the sine wave should cross the x-axis whenever it equals 0, which will be at every integer multiple of pi, that's what's happening here. But we have to think about this as 0 and then pi being 3.14 and 2 pi being 6.28. If we were to take every point x, y on the graph of the sine function and reverse the coordinates to get the corresponding points y, x, we would get a graph that looks something like this, which clearly fails the vertical line test. Now, when we looked at that parabolic example that failed the vertical line test, we had to cut off part of the original parabola so that the inverse would pass the vertical line test, making the original function have to pass the horizontal line test. This had to be done in such a way that the domain of the inverse still accounted for the entire range of the original function, and the range of the inverse was going to be some subset of the domain of the original function f. This means that the domain of the inverse sine function will be all numbers between -1 and 1. As for the range, the gods of mathematics, as I prefer to call them, decided to limit the range of the inverse function to angles between -pi/2 and pi/2 radians. This means that when you take the inverse sine of a positive number or a positive ratio, the answer you get will be some angle in quadrant 1 whose measure is something between 0 and 90 degrees or 0 and pi/2 radians. But when you take the inverse sine of a negative number or a negative ratio, you will get an angle between -90 and 0 degrees, or between -pi/2 and 0 radians. This is why when you take the inverse sine of 1/2, you get 30 degrees, or pi/6. And when you take the inverse sine of -1/2, you get -30 degrees, or -pi/6 radians. Now, the gods of mathematics did it like this because they wanted to make sure that whatever function they had that defined the inverse sine function could be continuous. And they wanted to be pretty straightforward, so they decided to cut off any angles that were bigger than 90 degrees or less than -90 degrees from consideration when trying to figure out what they should do to get this to pass both the horizontal line test and the vertical line test. So all these parts of the graph that I've marked here with dashes have essentially been removed, so the only parts being considered are those with solid lines. Here I've plotted some points on each graph, and you can see the relationship between them as the x and y coordinates are being reversed. But for all intents and purposes, the inverse function will only generate angles between -90 degrees and +90 degrees, or -pi/2 and +pi/2 radians. So while this sine function will continue going up and down forever and ever in both directions, the inverse sine function is just this small blue graph in the middle right here. So now let's look at what happens when we do this with cosine. When I graph the cosine wave, we see our regular graph starts at 0, 1 and decreases down in -1 when we get to pi radians, and then comes back up to +1 when we get to 2 pi radians. And this pattern repeats itself over and over again in both directions. Here, I'm going to insert the line y equals x, which will be our eventual line of symmetry for the inverse cosine graph. I forgot to do that with the sine function earlier. So the reflection of the cosine graph over the line y equals x is going to look like this. Again, just like the sine graph, it's going to fail the vertical line test. So we must cut things off in a way to get the domain of the inverse cosine to equal the range of the cosine, and the range of the inverse cosine to be some subset of the domain of the cosine function. So the domain of the inverse cosine function will run from -1 to 1. And the gods of mathematics decided for this function to go with 0 to pi radians, or 0 to 180 degrees, for the range of the inverse cosine. This ends up cutting off the graph to where you see the solid parts of the graph, and the dashed parts are going to be removed. Now you should be able to see by looking at this why they couldn't go to the negative angles, because if you look at the negative angles in quadrant 4, you're going to get the same measurements for cosine as you got in quadrant 1, and that would still fail the vertical line test. So as a compromise, the gods of mathematics went to quadrant 2. This gives them a nice, smooth, continuous function for both the cosine and its inverse. Here are some reference points on each graph. And I said we're limiting the inverse cosine's range to account for only angles between 0 and 180 degrees or 0 and pi radians. So even though the cosine wave will technically go in both directions forever, bobbing up and down between -1 and 1, the inverse cosine will be just this tiny blue graph right here in the middle. From a practical standpoint, the inverse cosine of a positive number or ratio will give you an angle in quadrant 1 between 0 and 90 degrees, or 0 and pi over 2 radians, while the inverse cosine of a negative number or a negative ratio will give an angle in quadrant 2 measuring between 90 and 180 degrees, or between pi over 2 and pi radians. This is why the inverse cosine of 1/2 will be 60 degrees, but the inverse cosine of -1/2 becomes 120 degrees, or 2 pi over 3 radians. Now, if you recall, we've already seen this behavior occur when we were looking at the law of cosines in section 6.6. When we were dealing with acute angles, the cosine values were positive, but when we were dealing with obtuse angles, the cosine was negative. Now let's look at the inverse tangent. Setting up its graph, we see that this pattern is going to repeat itself every 180 degrees with periodic asymptotes along the way. Well, this graph is already busy enough, so let's take some of those asymptotes out for a bit. There, that's better. Now, let's put in the line of symmetry at y equals x and flip this graph over sideways like so. Again, this graph fails the vertical line test, so we need to cut off part of the graph like we did before. We need the domain of f inverse to be the range of f, which means the domain of our inverse tangent function will be all real numbers from -infinity to +infinity. But we also need to set up a range that will account for everything and still not fail the vertical line test. Here, the gods of mathematics decided to use the same restrictions that they had on the inverse sine and go with -pi over 2 to +pi over 2. Although this time, because there's asymptotes there, and because the tangent of 90 degrees, the tangent of -90 degrees are undefined, we have to use an open interval instead of a closed interval. So by doing that, it's going to leave us with this highlighted portion of the inverse tangent right here in the middle. We can now remove the other pieces and turn them into dashed lines so we can show that they really shouldn't be there. In fact, let's just remove them outright. Here are some points on each of those graphs. On the red graph of the tangent function, you're seeing the different angles as your x values and the tangent ratios as your y values. On the blue graph, those coordinates have been reversed. So your x values are ratios, your y values are angles. It's also important to see that what was a vertical asymptote in the original function translates to become a horizontal asymptote in the inverse function once we flip it over sideways. Bottom line, The inverse tangent of a positive number or ratio will give an angle in quadrant 1 measuring between 0 and 90 degrees, or 0 and pi over 2 radians, while the inverse tangent of a negative number will give a negative angle between negative 90 degrees and 0 degrees, ending up in quadrant 4. So the inverse tangent of 1 will be 45 degrees, or pi over 4 radians, while the inverse tangent of negative 1 becomes negative 45 degrees, or negative pi over 4 radians. Now, I don't want to spend an incredible amount of time looking at the cotangent, the secant, or the cosecant, and I'm sure you can take some time on your own to explore these graphs on your own. However, based on the behaviors of the three primary trig functions, we should be able to predict the behaviors of the secondary trig functions and their inverses. I've set up a table which looks at all these three functions in one sitting, but I did not generate graphs for any of them. The cotangent graph will have a range that includes all real numbers, just like the tangent, so the domain of the inverse cotangent must also be all real numbers. Since the periodic asymptotes of the cotangent function occur at integer multiples of pi, the range of the inverse cotangent will be limited to angles between 0 and pi radians, or 0 and 180 degrees. Now, this is unusual when you compare it to the tangent function, but the preference of the gods of mathematics was to have an inverse that was going to be continuous over its domain where possible. Secant is going to behave somewhat like cosine. The range of secant, if you recall, is all real numbers not between negative 1 and 1. So the domain of the inverse secant is going to include only numbers greater than or equal to 1 or less than or equal to negative 1. The periodic asymptotes for the secant occur at odd multiples of pi over 2. So the range of the inverse cosine included angles between 0 and pi. So the inverse secant will have a range that will go between 0 and pi, but it will skip over pi over 2 to account for the asymptote there. For the inverse cosecant, the domain will be the same as the range of the regular cosecant function, where you're considering numbers that are not between negative 1 and 1. While the range of the inverse cosecant, just like the inverse sine, will include angles between negative pi over 2 and positive pi over 2, but not 0, because the inverse cosecant of 0 is undefined. So, summarizing the results of the table, the inverse cotangent and inverse secant will behave similarly in that the inverse cotangent and inverse secant of a positive number will give an angle in quadrant 1 between 0 and 90 degrees, while the inverse cotangent or inverse cosecant of a negative number or ratio will give an angle in quadrant 2 between 90 and 180 degrees. Meanwhile, the inverse cosecant will behave like the inverse sine in that the inverse cosecant of a positive number will generate an angle between 0 and 90 degrees, while the inverse cosecant of a negative number will generate an angle in quadrant 4 measuring between negative 90 and 0 degrees. This inconsistency with how the inverse trig functions are dealing with negative values plugged into them is why, when we were evaluating angle measures in reference triangles back earlier in chapter 5, I was insistent that we deal with just the positive ratios and then look at attaching positive and negative signs afterward based on whatever quadrant the terminal side of the angle lied in. This is because no matter which of the six trig functions you're working with, the inverse trig function applied to a positive number will always give you back an acute angle somewhere in quadrant 1 with a measure between 0 and 90 degrees, and we can use that as a reference angle to solve most of the problems. Let's see if you can try a few more of these, but this time without your calculator. Remember, the -1 in the notation is read and treated as the inverse, not the reciprocal of the function. And you never want to treat it like an exponent. Here's some you can try on your own. Go ahead and pause the video to see if you can evaluate these expressions without a calculator on your own. All of them are tied to special angles that we've been studying for our mad minutes. So the reference angles are all 0, 30, 45, 60, or 90 degrees. See what you can do and we'll regroup in a bit. So the inverse tangent of the square root of 3 over 3 is going to be 60 degrees or pi over 3. The inverse cosecant of the negative square root of 2 is going to be negative 45 degrees or negative pi over 4. Remember, the inverse sign of its reciprocal, negative 1 over the square root of 2, or negative square root of 2 over 2 after we rationalize, will be negative 45 degrees. The inverse cosine of negative square root of 3 over 2 is going to be 150 degrees or 5 pi over 6 radians because, again, for inverse cosine, we want to go to quadrant 2 to find that obtuse angle which has the negative cosine value. The inverse tangent of the negative square root of 3 over 3 is going to be negative 30 degrees or negative pi over 6. The inverse secant of 2 is going to be 60 degrees because the secant will equal 2 whenever the cosine equals 1/2. Finally, the inverse sine of negative 1 is going to be negative 90 degrees or pi over 2 radians. Now we're going to look at a few unexpected results that you're going to have to pay attention to when combining f and f inverse when it comes to trigonometric functions. As we discussed at the beginning of the lesson, normally when you apply the inverse to the original function, everything cancels, you get what you started with. However, because of how trigonometric functions have highly restricted domains in order to be invertible, this isn't necessarily going to be true. Here's a couple of examples. If we were to take the inverse sine of the sine of 2 pi over 3, one might think, jumping to a quick conclusion, that the answer is going to be 2 pi over 3. However, it's not. The sine of 2 pi over 3 we know is the square root of 3 over 2. But the inverse sine of the square root of 3 over 2 ends up back in quadrant 1 based on how we had to restrict the range of the inverse sine function so that the answer will be 60 degrees or pi over 3 radians. Similarly, if we were to take a look at the inverse tangent of the tangent of 3 pi over 4, we start by working on the inside, knowing that the tangent of 3 pi over 4 is negative 1. Now we're asked to find the inverse tangent of negative 1. The inverse tangent of a negative number always gives an answer between negative 90 degrees and 0 degrees. So the answer here is going to be negative 45 degrees or negative pi over 4 radians. Now, as a general rule, when it comes to looking at the homework, since the problems here started out with radians, it is probably best to enter your final answer back in radians. Now, I'm giving out these answers in both degrees and radians partly because I understand that radians are still a fairly new idea. But you do want to pay attention in WebAssign regarding what they're looking for in their final answer. Sometimes it's okay to write the answers in degrees. Other cases, you will need to write your answer in radians. Let's look at a few where we might be intermixing functions. Suppose I asked you to take the inverse sine of the tangent of negative pi over 4. As a general rule, based on the order of operations, you always want to start on the inside of the parentheses first. In the first example, the tangent of negative pi over 4 is negative 1. So when we compute the inverse sine of negative 1, we'll get negative 90 degrees or negative pi over 2. In the second example, you're looking at the cosine of the inverse sine of negative square root of 3 over 2. The inverse sine of negative square root of 3 over 2 will be negative 60 degrees, or negative pi over 3 radians. The cosine of that angle will become positive 1/2, because again, the cosine of these negative angles in quadrant 4 are actually going to be positive based on our all skiers take chances, all sine, tangent, cosine rule. What if you run into some where you are asked to intermix the function, but the values you're working with are not coming from one of our special mad-minute angles? Let's look at one just like that. Suppose I ask you to compute the sine of the inverse cosine of 3/5 without a calculator. Now you're thinking I'm just being crazy because how are you supposed to know how to do the inverse cosine of that without a calculator if it's not a special angle? Here's the trick. We're going to draw a reference triangle that satisfies these conditions. By asking what is the inverse cosine of 3/5, we want to know what angle has a cosine value of 3/5. In order to figure it out, let's try drawing a picture of it. Here's that reference angle where the cosine adjacent over hypotenuse is going to be 3/5. The angle in question I've marked with a little Greek letter phi here. So now we can rewrite our problem in terms of that. So what I'm looking for now, by asking what is the sine of the inverse cosine of 3/5, I'm really looking for the sine of that angle phi in that reference triangle. Now, what makes this problem simpler than it appears is that I don't actually have to find the measure of angle phi to solve the problem. What I do have to do is find the sine of the angle, which will be the ratio of the opposite side to the hypotenuse. The opposite side has length 4, not just because I labeled it up here, but it can be very quickly verified by using the Pythagorean theorem that the y value has to equal 4. Assuming that we're in quadrant 1, I don't need to worry about the positive or negative sign either. So the sine of angle phi opposite over hypotenuse is going to be 4/5. Let's try another one. Suppose I'm interested in finding the tangent of the inverse secant of 13/5. The secant is the hypotenuse over the adjacent side. So I can construct a reference triangle that will have a hypotenuse of 13 and an adjacent side of 5. This time, I've marked that angle with a beta, but you could measure it with a theta or a phi or an alpha or whatever angle you feel like. So what I'm interested in is the tangent of angle beta, which will be the opposite over the adjacent side. The opposite will have length 12, which again can be easily verified by using the Pythagorean theorem. So the tangent of angle beta is going to be 12/5. And we were able to do that without using a calculator to figure out what angle beta was, because again, we really don't care what angle beta was. We're more interested in that relationship between the three side lengths. Of course, you're probably thinking, you know what? I'm doing this from home. You can't stop me from using my calculator, so I'm just going to do all these problems on my calculator. Well, what that's going to force me to do is to start creating problems that can't be done on your calculator. Problems where you're going to have to construct a reference triangle to solve for them, and problems where the answer isn't going to have a simple numeric result. Here's a good example of one you might see on a homework or on a quest. Write an algebraic expression to describe the following. We want to determine the sine of the inverse cosine of x. A hint that I'm giving here is to draw a reference triangle, but the question might be, how am I supposed to do that? I'm not given any real side lengths here. Well, you don't have to have them. Remember, when you're taking the inverse cosine of some value x, what you're getting out is some angle, which I can call theta. For simplicity's sake, let's try to construct that reference angle in the first quadrant where theta is being measured from the positive x-axis to the terminal side of the angle in quadrant 1. If we're saying that the inverse cosine of x is angle theta, then equivalently, the cosine of angle theta must equal x. Of course, normally, we think of the cosine as the ratio of the adjacent to the hypotenuse. So perhaps we should rewrite this ratio where cosine of theta equals x over 1. This is going to imply that in my reference triangle, my adjacent side is going to have length x and my hypotenuse will have length 1. The opposite side, by using the Pythagorean theorem, will simplify to the square root of 1 minus x squared. This is because what you have is x squared plus y squared equals 1. So rearranging the terms to isolate y will give you this result. So going back to our question, the sine of the inverse cosine of x will be the sine of this angle theta that we see in the diagram, and the sine is computed by taking the opposite over the hypotenuse, which will give us the square root of the quantity 1 minus x squared all over 1. Let's look at one more before we wrap this up, and perhaps you can try to do this one on your own. We want to find the tangent of the inverse cosine of 3 over x. Again, Inverse cosine of 3 over x is going to give you some angle theta whose cosine is going to be 3 over x. So try to construct a reference triangle on this one and use the Pythagorean theorem to solve for the missing side. Once we have that, we can evaluate the tangent. Pause this video and try this one on your own for a little bit. All right, so here is our reference triangle, and here is the angle theta that we're interested in. Because we're defining the cosine of theta as 3 over x, the adjacent side will have a length of 3, and the hypotenuse will have a length of x this time. Working this out with the Pythagorean theorem, if 3 squared plus the opposite side squared equals x squared, then the opposite side will have a length of the square root of x squared minus 9. Now that we have that in place, the tangent of the inverse cosine of 3 over x is going to be the tangent of this angle theta described by the reference triangle here, which when you look at the opposite over the adjacent side, you should get the square root of the quantity x squared minus 9 all over 3. So we've managed to cover two sections of material again, and for the most part, the content between the two sections is identical. Why the author didn't think to combine the two sections into one is beyond me, but this is what we're looking at. As long as this presentation was, the material from the homework is actually quite straightforward. Mostly, we're looking at doing mad minute type problems backwards. I'm not going to ask you so much to look at the graphs of the inverses or do anything involving the basic shapes of these graphs, but I had to put that stuff out there to make sure you realize where it was all coming from and that there are specific rules that have to be followed when working with inverse trig functions. If you're working on some problem where you're allowed to use your calculator will generally always put the angles, especially when working with negative values, will put the angles in the correct quadrants for you. Here are the problem challenges for sections 5.5 and 6.4. Even with as many questions as there are, it won't take you that long to go through both of these problem sets. As always, if you have any questions or worries about these, feel free to contact me via email or post your question on the discussion board. Thanks for watching, and we'll see you all soon.